Cool, thank you all for bearing with me. So, this is my talk about PostgreSQL called Frequently Delivered Answers. And this basically comes about from the idea of DevOps. I'm most definitely operations staff. I've done Linux systems administration for 17 years and been a Postgres DBA for 12. Worked for a lot of small companies, and sometimes I get thrown into, oh yeah, the developers don't have any time. Here, we're going to need you to write this. So I go, bah! And then I go grab a bunch of Perl modules and throw something together that's occasionally considered suitable but semi-horrifying. And then sometimes developers need to do various bits of operations work. And yeah, Postgres can be a life preserver for you in the same way that Perl is for me. And Postgres is pretty high performance, handles hundreds of terabytes, petabytes. Yahoo had the largest data warehouse in 2010, 2011 that was several petabytes built on top of Postgres. It's feature rich, it's ASIC compliant, it's got a lovely ecosystem of tools, it's well supported by Perl, DBI's class. You can even write your own stored procedures in PL Perl, which actually works out really well. And plus, there's elephants, and everybody loves elephants, right? Now, things that I frequently hear from developers that I've worked with is that Postgres is very hard to configure. And that it needs a lot of ongoing maintenance, and it needs a lot of hardware to get good performance, and I don't like SQL. So, most of the time in the office, I have this book by Marcus Wining called SQL Performance Explained. And once they've read through that and they've worked with a bit of Postgres, they actually seem to like SQL after this. So, anyway, those all are just horrible myths as far as I'm concerned. You can do some really quick out-of-the-box configuration. There's a lot of quick and easy performance boosts and just random traps that you can avoid. And Postgres does need ongoing maintenance, but not all that much. So, first thing that I always do if I have a new Postgres instance is you have to turn on logging. You are flying blind without this, without logging at all. It's largely low overhead unless, for some reason, everything is sharing the same disk, or you have like a crazy amount of transactions per second. We're talking like, 10,000 or more transactions per second. In which case, then, you turn on full logging for everything, and suddenly, in 10 seconds, you get like a 100 megabyte log file. So, anyway. You can integrate this into your logging system by syslog. You can create CSV formatted logs, which I tend to do for my personal development, like on my laptop. And then I can do things with text CSV and just pull it into little pieces. And then for production, I tend to use something like PG Badger or PG Thween, which take a standard format log and they'll create a report for you of like, these are the most run queries that you have, and these are the average time it takes. This is the number of lock weights, number of size of temp files, all these sorts of things that you can start to use to make improvements to your system. So, incredibly handy. So, for basic setup. Log destination. So I took this from my laptop, so it's a CSV log. You can choose standard error for the standard format log, or you can do syslog and it will log directly to the local syslog name. I tend to stick everything in varlog, and on Debian systems, because you can install multiple versions of Postgres side by side trivially. The devs support that very well. I tend to name them per version. Also, turn on the logging collector, of course. And then I tend to log the file name as just Postgres or whatever. The %a is the string format. So Postgres name of day.csv, log rotation age 1 day, which after day it rotates it, log rotation size 0, which says don't rotate this based on its size, just rotate it based on time. And for my laptop, or for places that have smaller disks where the logs live locally, I have them truncate on rotation because by that time, by the time a week rolls around, they should have been very much into the remote central syslog system. So you can turn that on or not. Okay, so now you start getting into a little bit more of the visibility here. So you can look at the log min duration statement. I tend to set this to 250 milliseconds. Depending on like what your database is doing, you can set it higher. For like a data warehouse, it could be up to like 5 minutes or something, and that would make sense. But I find this to be a good general OLTP starting point. If something takes more than a quarter of a second, people are going to start seeing the slowness on load. Okay, so you're going to want to log checkpoints too, because you want to know how often Postgres is writing to disk, and this will tell you. Connections, you want to know when apps connect and what they're doing, and when they disconnect. And then log lock waits. You want to know if something is holding on to a tuple, or if you've taken out, you've explicitly defined a large lock across your tables, and that's slowing other things down. That will show that. And then log temp file 0 says always log the size of your temp files. This is a great way to start out, because temp files, once you get over a certain size of memory, it starts to spill out to disk, and that is remarkably slow. And then log auto vacuum in duration. So this will tell you what the auto vacuum daemon is doing, and whether or not you need to do any tuning with it. But normally out of the box, you just want to see what it's doing. And then you can define the log line prefix. I use this one generically, which, and it's slightly different than the string format time, because this is a Postgres specific thing. So the %a is log the app name, and then u is user at host : port, what database it's connecting to. If this is an automated process, the queue makes it stop right there. But if it isn't, like if this isn't something like the checkpoint daemon or the auto vacuum daemon connecting, it will show you the process ID, transaction ID, and timestamp with milliseconds. So it gives you a lot of visibility, just really quickly. So now that you've got logging turned on, you can start to look at the memory parameters. Shared buffers is an area of memory that Postgres has defined and taken up, and it uses that to load its data off of disk and to process it and do other things. Work memory is what you use for things like sorts and various, most of the time it's for sorting something. There's a couple of other things it's used for, but that is the major thing that you'll run across. Maintenance work memory is used for creating indexes and also affects auto vacuum. And then there's the effective cache size, which basically hints at how much of your database can be in the file system cache. So, shared buffers. If it's under 2 gigabytes, like on Raspberry Pi 3, set it to 20% of the memory. So one of the things that frequently comes up is you need like lots of hardware to run Postgres. It's totally not true, because one of the build farm members, Hamster, is a Raspberry Pi 3. I've run Postgres up to 9.2 on a Debian PowerPC G3, 300 megahertz with 192 megabytes of RAM, and it worked just fine.
How long did the build take? How long did the build take?
I didn't build it from source, I just installed it from the Debian repository.
Okay.
So, yeah, and it did its thing. And then up to 32 gigabytes of RAM, set it to a quarter of the system memory. And then if you have over 32 gigs, set it to 8. You can set it higher depending on what you're doing, but then you start needing to balance, like, okay, I'm starting to overflow the translation look-ahead buffer with the CPU, and start to get interesting bits of OS contention, and then that just gets really complicated. Yes?
Is there any part of the logging that can help me determine what a good shared buffer size would be? If I need more, or if I'm already far above what I actually need?
There is a thing called PG buffer cache. That's an extension where you can look and you can see how much of all your tables are in memory and used, and it will give you kind of a summary of, like, okay, most of these I'm hitting on a fairly regular basis, so it doesn't make any sense to add this. Or, there are some of these tables that don't have a very good hit ratio, so adding more RAM might help. This is actually in the default Postgres contrib, so you can use that to determine if you want over that. So, cool. Work memory. This defaults to 16 megabytes, which most of the time this is okay. You can make it 32 to 64 megabytes generally pretty safely. But the best measure of it is to actually use the logging we just turned on, because it's always better to know than guess. So you find the largest temp file in there, because we're logging all the temp files, and multiply it by 3, set it to that. That'll actually work really, really well. If you happen to need more than that, you can actually set this per query. So, like in DVDPG, you can do like set work memory to some ludicrously large number for that particular transaction, and then do your thing, and then reset the work memory back to what the default is. So you can change it on the fly if you absolutely need to as well. But don't set this to something ludicrous, because this is allocated per sort, and if you have a bunch of sorts in a large query, it will eventually push things out of cache and just be a drag on your performance, which is not good at all. So maintenance work memory, generally set it to 10% of RAM, max of 2 gigabytes. This is because there's this interesting thing in the code where if it's bigger than this, it just gets set to 2 gigabytes. I think that's going to be addressed in 10, so this will probably change. Vacuum uses this to pull as sort of a scratch area when it's running over the heap and twiddling tuples and rearranging things. And create index uses this, like, okay, here's a batch, 2 gigs, here's a batch, 2 gigs. So that can help immensely with your vacuum performance and reduce vacuum I/O and the overhead of create index. So, and then the effective cache size. Set it to about 50% of system memory. Or if you've had this database for a while and it's been running, and you look at the output of free. So basically, you want to set this to about what the file system cache is using on an entirely, basically, if Postgres is the only thing running there, just set it to that value, because that's basically everything in the file system cache, which is Postgres. So, and this is a suggestion that helps the planner determine whether or not it's better to do like a sequential scan or a random scan, walk and index, which is random I/O. And this isn't allocated, and that tends to trip people up. So now the next important part after you dealt with memory is checkpoints. These are when Postgres goes through the write-ahead log. It initially writes out to the write-ahead log, and then when a checkpoint is called, it replays everything from the write-ahead log and writes it out to the base data files. Back in older versions of Postgres, you could get these horrible things that were called checkpoint storms, where suddenly a checkpoint would be called and then the database would basically go out to lunch for a bit, while all of the I/O just was soaked up writing out to disk. So there was a lot of effort that has gone into being able to tune and tweak that. So wall buffers, 16 megabytes, how much of a wall file will you have kind of buffered in RAM? And that's basically a segment. Checkpoint completion target, how far along do you have to be in the current checkpoint to look at starting another one? If you have data that's very, 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 very frequently updated, like if you're saving like a stock ticker or something, you make that lower so that things will hang out in the shared buffers longer. You're not writing out a whole bunch of different updates. But most of the time setting it to 0.9 will make everything, the idea is to make this even and smooth and a very steady, predictable load on your I/O subsystem. And then start out with checkpoint segments at 32. Now, and in 9.5 and later, they changed checkpoint segments because people found that to be very confusing. So you can set a minimum size for the number of wall files and the amount of disk space they take up, and a maximum size, and this helps DBAs and sysadmins because a lot of the time you'll have a separation of, okay, the OS is on a RAID 1, the transaction log directory, the wall log, is on another RAID 1, data is on a RAID 10, and then you have temp files and other stuff on an SSD. So you've broken up all of this I/O, and you want to know how big disks do I have to buy, how much do I have to spend, am I going to be wasting a bunch of this? So this helps with that. So now we go back to the logs again. If you're doing like a giant bulk load, or you're doing a bunch of testing, or you're trying to do some you basically load testing. It'll give you this thing, a message along that like checkpoints are happening too frequently, consider changing the number of checkpoint segments or the checkpoint timeout. So it will squawk very loudly in the logs, but only if you log checkpoints. So, and the whole point of that is to go and go, okay, for my load, I actually need these bigger. There isn't a whole lot of penalty except for extra disk space and longer startup time for having more segments than you actually need. But yes, again, the whole thing is not to beat up your I/O subsystem. Okay, so for the planner, you can help it with a few hints. There's this relatively cryptic thing called effective I/O concurrency that I've done a lot of experiments with and other people have. And it's basically the number of concurrent disk operations that your array can handle. If you have something like a SAN or whatever, you can set it to the number of I/O channels. If you have one of those luscious, ludicrous NVMe drives, the PCIe ones, just look through the documentation, figure out what the queue depth of that drive is, and just set it to that, and then you'll be really happy. Or take half the disks in your RAID array and set it to that. Now, random page costs. Okay, so there are all of these costs in the Postgres config. Most of the time you don't have to tweak them, but they are all in terms of how much it costs to do a sequential scan. So generally, sequential scans are set at 1.0, and random page cost is set at 4.0. Depending on how good your I/O subsystem is, or even sort of how bad your I/O subsystem is, it can cost you very little to do an index scan, which is looking at a random page. So most of the time, if you have a nice RAID 10 array, you set it to 3.0, and you'll get lots of great sequential throughput because spinning Rust disks are really good at that. SANs can do a little better with higher bandwidth, so you can set it lower, and it's not quite so bad with the random I/O. Same with an SSD, and 1.1 for the EBS at Amazon because it's going to suck either way. Okay, and for basic tuning and configuration, that's it. That's all you really need to do to actually have a pretty reasonable, pretty performant Postgres install. Except there's a couple of things if you want to do some interesting future proofing, which is turn the archive mode on. This is a parameter that you have to restart the entire daemon to enable. And this lets you start shipping transaction logs elsewhere. So, and you can do that with a specified archive command. You can fill this in with a script that you've written, or there are things like Wally or OmniPetter or PetterTools or anything. But right now, we're just basically setting that to this colon, which is a shellism that goes. It's more portable than just setting it to bin true, but it comes out to the same thing, because if the archive command doesn't return true, wall segments don't get recycled, and then you run out of disk space, and that's really bad. Archive timeout, if you want to send a segment along and switch at a particular time for an SLA or whatever, set this to something like 60 seconds or whatever. But right now at 0, it doesn't time out for anything. You can actually change that one on the fly. Wall level, there's a minimal archive, hot standby, and logical for all of these. The one that will allow you so as you go up in that from minimal to archive to hot standby to logical, more and more data actually gets put into the write-ahead log. So if you don't need it, then that'll actually save you a bit on I/O because there's automatic wall compression for you. But this one allows you the most flexibility because you can do a wall archive and you can do a hot standby. And then these two are only valid for 9.3 and later because of streaming replication. And these are the wall senders, which are these little processes that ship wall records. And then replication slots, which are the number of other connections that can be, the number of incoming connections that can be made to access replication level events, and I'll get to more into what that means here in a bit. Okay, so, and in general terms in performance, there's a bunch of quick and easy wins and things not to do. Linux has this really, really, really unfortunate thing called the OOM killer. And occasionally, you know, it's there. Under memory pressure, it will randomly murder a process to try and keep the system up. It occasionally will murder a process that's really, really important, like Postgres. The whole point of the machine is Postgres taking up memory, and if it hits that, it doesn't like it. It's a little like being in a plane and realizing it's like slightly over capacity, and rather than dumping out something to extend the runway, something else, something unimportant like, you know, throwing out a bunch of trash, it's like going into the cockpit and shooting a pilot. So anyway, turn that off. It's really bad, and this will do it. Okay, and then for performance, 99.9% of the time you want to use copy instead of insert for bulk loads. There's very rare times where you might want to do that, but yeah, those are special snowflake circumstances for the most part. So inserts are really, just bare inserts are really slow because they have an implicit begin commit wrapped around them as you're doing it. Begin and then doing a whole bunch of inserts and then commit is faster because all it's doing is, okay, I'm going to mark I'm going to make a whole bunch of wall entries, and then I'm not going to actually say that we're going to do anything with these until you hit commit. And then there's copy, which is this interesting sort of binary bulk loading that's based on a well-documented tab-separated value format with well-documented escape characters. So all very consistent, all very fast, all very tuned, and some very nice C. Also, DBDPG supports get copy data, put copy data, and put copy in, which I have used on occasion to do multiple book loads at once, which was awesome when I needed to do it because I was really desperate. Okay, so for performance, good indexes have a really high selectivity on commonly used columns or a constraint, and that means that good indexes have largely unique values in them because basically it's just a B tree pointer for the most part. And for indexes, only the first column and a multi-column index can be used separately. So you have column 1, column 2, column 3. If you do where column 1 equals foo, it'll use the index for that. If you use column 1 equals foo and column 2 equals bar, it will still use that. If you use column 2 equals elephant, it won't actually use the index in that case. So you can use them in basically any combination so long as it includes the first column or the last two, but you can't use each one of them individually unless it's the first thing in the column. So basically match the index order to commonly used queries and their where clause contents. If you're not sure how this is being used, be sure to do it in a transaction, especially if it's like a delete or an insert, because it will actually do it if you do an explain analyze, but you'll need to do an explain analyze because it will tell you the difference between what the planner thought it would do, because there's the estimate and then there's the actual cost, and if those are really off, then you either have a problem with your statistics or the way that the query is written, so you can start to use that to iterate on, well, why are we doing this? And all of these things are, I think, really good to know for developers, because honestly, developers have the best idea of how they're going to be querying this data. They've talked with people, they've got the business requirements and everything, and if they've gone through all of this work, why not just, just tell me what index you have, or I'll give you the permission to make an index there. So, excuse me. Anyway, developers, I feel, are way better to tell me what indexes are needed than having to do a bunch of log analysis. And then there's, for the most part, don't do these. You can do them and they can work. It's just things that are like, okay, you really need to think about what you're doing in your data model if you're thinking about doing something like this. You basically use your database as a file system. There are people who will put large binary objects inside of the database, and those can be very, very slow to query out, but sometimes it's better than adding a bunch of extra complexity into the system. or keep very long transactions open. So generally, you keep a transaction open, you transaction 1 and it tries to grab, say, tuple 1, and then another transaction comes along and wants to update tuple 1 too. So it's going to have to wait on that. Also, the little auto vacuum process will wait very patiently, because it's not supposed to block anything, to wait for that tuple to be released by that transaction. So that affects vacuum, that affects concurrency, and generally results in a poor performing database in general, because it's not living up to its throughput and the maintenance isn't being done. Task queues, where you have a bunch of things that are being updated and over and sort of being kept track of in this giant historical table. You can do it, but again, that's going to require extra tuning, extra maintenance, and a lot of extra effort. And then frequently locked singleton records have similar problems with concurrency where they just block everything. Sometimes those are really useful for things where you absolutely have to have like consistency in things. Like if you need a gapless sequence, you can do this. But I've only ever seen that done in financial applications. Mixing a workload. OLAP and OLTP have wildly different needs. OLTP, you just need to be throwing things out. OLAP, you need to be expanding things out hugely. Also don't use a large in clauses, because you end up doing a large index scan and a bunch of nested loops, and that's just killer on performance. And then unanchored likes, you can't use an index with them, so that's bad. Looking at your logs will tell you where query timings and things are slow. Like I mentioned earlier, PG batter and PG for wean will go over everything and let you know. You can also use an extension that's included with Postgres called pgstat statements. It will put it into a table and let you look at everything. You can query that. It doesn't have like super good statistics, but it's all being worked on. And then there's auto explain, which is awesome because you have to load a shared library, but if a query goes past a particular threshold, like your 250 milliseconds, it will automatically explain the entire query and put it in your log. And this is an easy way of looking. Explain can't really give you a good idea of what's going on inside of the function, because you'll basically get like function scan and net, and then it won't tell you anything useful. This will actually tell you what's going on inside of like your PLPGSQL function. So you can use that to tweak your stored procedures. And then for basic maintenance, basically don't shut off auto vacuum. It's really there to help you. And then you don't have to think about it, but if it's causing problems like increasing I/O or whatever, do a manual, at the very least do a manual vacuum off hours. Otherwise, you're going to have a bunch of bloat because of MVCC, which is where basically, like we do an update, Postgres under the hood will just turn that into, I'm marking the previous tuple dead, I'm copying the new one with the new value over and saying it's alive. And then vacuum comes along and goes, okay, you are dead. All right, I'm going to scribble this out and you can be used later inside of the data file. There's also the transaction ID wraparound, which is basically this ring buffer of 32-bit integer. And that's used for transaction visibility, and if that gets up towards the 2 billion and change limit, the database will shut down and force you to start it in single user mode until the vacuum has finished that will move all of the transaction IDs around. This also helps keep disk space under control, because you'll have a bunch of dead tuples in there that are just taking up space. So you want to do that anyway. And then when you're running auto vacuum, it'll do auto vacuum, it'll do auto analyze, it'll keep all of the statistics up to date so the planner knows exactly what it needs to do. Otherwise, you'll get some really bizarre query plans. Okay, then a little bit of security. Keep your list and addresses local and internal if possible. You can filter things with the PGHBA conf. You can limit database connections and users. And you can use that for various roles along with grant and revoke and firewall roles. I use firewall rules all over the place too. Okay, only you can actually connect here, which gives an extra layer of security over and above the pghba.conf.
10 minutes.
10 minutes, okay. So, all right. That's basically everything you need to know for a very happy setup. And you can just stop there, or you can start to do other things. So, there's a lot of convenient things about Postgres. It's kind of this platform unto itself. Contrib is full of goodies. I'm very fond of PG Crypto for various reasons, because some of my devs are a little nuts. PGXN has a bunch of extensions that people have found useful. It's modeled after CPAN. David Wheeler started it, Theory. So one of the things I did was I made my very own user-defined type for a password. And I made comparator rules for it, for equality, left equal, right equal, all of that. And made a hashing system based on the blowfish bcrypt. So, and then a function for authorization where it was like, don't do anything clever, just throw the username in here, and it will give you a true or false at the end and tell you if they're authenticated or not. Offloads work from the developers, so they don't do things like add the app number and the username and then MD5 everything. Yeah, this has its own security considerations because in the logs, depending on how it's implemented, you can see bare passwords in them. And if somebody takes over the Postgres system, if your Postgres system gets hacked, they can read those passwords, but generally, at least in my case, if they're on the database server, they're screwed. I'm totally screwed. So you can make your own domain-specific data types. You can also make use of a rich set of these other built-in data types. HStore is a little key value store type, so you can just use it for a bin of things and just do key value accesses. It's very easy to index. JSONB is binary JSON format, so I mean, if for some reason you had this crazy idea to use Mongo, you can go, hey, you know what, instead I think I'll use JSONB. Or, and if you're using Java, you can do a bunch of interesting things with XML in the database, and there's an actual XML type. And then there's streaming replication. Good for high availability disaster recovery. It involves extra servers waiting there, except when you can actually use them even when they're sitting there. And then this is a frequently given answer to management. So, oh, these are sitting here just for some magical disaster time. Well, you know, also the developers use them because you can take snapshots from them and then develop against that. And oh, also, while the developers are using this and they're happy and we're finding bugs with QA before we do rollouts, they're testing the backups too. So it's very easy in 9.4 plus to set up replication. Replication used to be a pain. This is actually pretty easy. And it streams individual role records, so you can do it over WANs instead of just your LAN. So basically, you just provision another database server, stop Postgres, remove the basic initdb directory, add these on. So hot standby means you can actually query it while it's replicating. You can't write to it, but you can read it. Hot standby feedback will say, okay, this query's running here, so don't vacuum these on the master. And then wall senders and replication slots, because you can start to do other things with your first replica, like cascade them. So all you really have to do is paste something like this in the recovery.conf. So turn on standby mode, tell it what slot name it is, because you can name these, so make it descriptive. What host are you connecting to? username, password, SSL mode, and then a little file that you touch to actually bring it up into standalone mode. So put in a pghba.conf entry. This is one that I use a lot. So basically make a user make this entry. Do receive xlog. You can tell this to create the slot, which is important because when the slot's created and the slot's been in use, the wall won't be recycled, so you won't miss anything, and this can just pick up and be very easily used once you're done. So you take your base backup, which basically copies over all of the base files from the primary server, put in the recovery.conf, start it, and since you turned on all the logging, it will tell you exactly what, if anything, that you've done wrong, and you'll be able to fix it. And then I generally do a quick test on the primary, which is just this little create table, and then select random, so it puts a bunch of random numbers in and generates a whole ton of wall traffic. And then I look at the lag from pgstat replication, because it will tell you the logical sequence number on the primary and the logical sequence number on the secondary for that slot, and if those match up, then everything has been replicated just fine. And they are up to date to the last logical sequence number. So now that you got this set up, you can put it to work. You can take base backups from your secondary, which is beautiful, because you don't have to affect any I/O or connections or anything else on your system, on your main system. And so just take your base backup with a command like this. You can set up a pg receive xlog somewhere if you want to pull in the write-ahead logs and use point-in-time recovery. You can also use things like omnipitter or wally, or you could actually just do a plain logical pg dump. All of this is really good because it takes load off the primary server and basically justifies the existence of your replica. You can have them in multiple data centers. I have them in like 6 of them spread across the United States. We use it for regular refresh of our staging cluster. QA won't even bother to test code changes after having done this for long enough, unless the database has been updated, because we've caught so many bugs in code just from knowing, oh yeah, no, this isn't a data thing. This is definitely a code bug because we just took a snapshot of the database. You can also delay a replica doing this, but make sure to turn off hot standby feedback or you'll bloat your master. You can guard against the errant drop table or where list delete. This has actually come up a couple of times. And this meant that it was 5 minutes of downtime instead of the 3.5 hours it would have taken to restore the whole thing from backup. So, in closing, just a few of these little tips and tricks go really, really, really long way to making your Postgres setup, maintenance, and just life simple and easy. So, questions, people, comments?
That's slides. Slides are online.
Oh, there will be. I'll make sure to put them up. I'll also make sure to go through and pull out like the little log bits and all of the config stuff, because for my developers setting up their own local development instances, I found it was really handy just to have all of that and tell them to paste, just take this out of the wiki and paste this in the bottom and you're good to go. So, all right. Thank you all.